Okay, last time we were discussing graphs, and I covered the basic concepts of graph, a few definitions, and the storage mechanism, the data structures which we use for storing the graphs in memory. So in this lecture we will be doing a case study, an example of graphs where we will be solving a real world problem using graphs. And please note that this particular lecture consists of a few of key definitions, so you have to be listening to this lecture very carefully, and there are around 3 or 4 definitions of various concepts to be covered in this lecture. So please listen to the contents carefully. Now, the problem which we want to solve here is that of traffic light problem, right? What is the traffic light problem? For example, this is an intersection, and we want a traffic signal to be placed here, right? Now what will happen that at a time we will open this this road, right? We will open this road and this green will be open. Okay, let me draw an arrow. Like this road will be open, and these roads, this road, and this road will be closed, right? For example, people who are on this road, they will be able to, and this road as well will be closed. They will be able to go here. They will be able to go here as well. They will be able to go here, and maybe they will be able to go here as well, right? Then once this turn is done, right? Then what we will do, we will open this road, and rest of the roads will be closed, right? So this is the typical system of a traffic light. But for example, if you open this this road for, let's say, 1 minute, and you do this opening of signals clockwise, in the worst case, for example, when you are here, for example, this is you waiting here for the signal to open, right? So you will wait 1 minute for this one, then this line will get green signal, then this line will this line or road, whatever, will get green signal, then this road will get green signal, and then it's your turn. So on an average you will be waiting for 1, 2, 3, 4 minutes, right? But the issue here which we need to solve is that we need to identify such turns. For example, when this road is open, maybe simultaneously we can open this road as well, right? So we need to find a set of turns. For example, this going from A to B is a turn, going from A to D is a turn, going from A to C is a turn, right? So we need to find a set of turns which can be executed in parallel, right? Okay, let me redraw this thing. For example, this A to B, let me draw it like this, A to B, it's a turn, right? Similarly, A to C, this can be executed in parallel, right? But right now the turn E to B, like while you have opened the turn A to C, and at the same time if you open this turn E to B, this is going to cause collision, right? So the issue here is to find all such turns that can be opened simultaneously. So when multiple turns are open simultaneously, remember a while ago I told you that you are here, you are waiting for the signal to open. So you were supposed to wait here for 1 minute, 1 minute here, 1 minute here, 1 minute for this signal, then your turn comes. So on an average you are waiting for, let's say, 4 minutes. But if we open multiple turns simultaneously, there is a very good chance that we decrease this wait of 4 minutes to maybe 2 minutes or less, right? So the objective of traffic light problem is this one, right? And here by turn, it's not that going from A to B is turn, going straight like from A to D, or coming from D to E is also treated as a turn, right? Now, how will we transform this problem into the graph representation? What we will do is that we will first of all list all the possible permitted or preemptive turns. For example, when you see this road map, these arrows on road E and road C indicate that these roads are one-way road, right? For example, you can go from D to A, you can go from A to D, no problem, right? And similarly, you can go from E to B, but you cannot go from A to E because this road E is one way. Same goes for road C as well. So this is the constraint in the problem. So to transform it into the graph, we will first of all identify all the permitted turns which we have in this problem, right? So these are 13 permitted turns which can happen in this road network. For example, if you see EB, it means that you can go from E to B. This is a turn. We are not saying that it can happen simultaneously with any other turn. We are just listing these turns. For example, you see DC. So from D you can go to C. Like this is a permitted turn, right? So on and so forth. So finally we get 13 turns which are permitted. Now what we will do, we will make a graph which will have 13 nodes. Actually I'm trying something. Okay, it's not happening, sorry. So which will have 13 nodes. Okay, for example, node 1, node 2, node 3, node 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So these are 13 nodes. Now next we will identify all the turns which can not or should not be allowed simultaneously, right? For example, if we open the turn from A to B, if we open the turn from A to B, and we open the turn from E to C. Now these two turns can be opened simultaneously, so we are good with that, right? No problem. But if we open, sorry, yes, but if we open the turn from A to D, at the same time we open the turn from E to B, so this is for sure going to result in a collision, right? So once we have identified the turns, 13 turns, we need to identify those turns which cannot be opened or allowed simultaneously, right? So what will we do is we will have 13 nodes, right? Okay, for example here we will have 13 nodes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? Each node will represent what? Each node will represent one turn. For example, this node represents this turn, this node represent this turn, and this node may represent this turn. Like for your convenience, you can put the label inside it, right? You can write okay, A, D, so on and so forth, right? So once you have these 13 nodes, Then, and each node represents a turn, you need to draw a line or draw an edge between two nodes. Now the question is that between which nodes or which turns you will be drawing or connecting the turns. So you are going to connect such two turns which are not allowed simultaneously. Right? You will get a complete graph. For example, this is the definition of the graph I have already told you. So we will be drawing an edge between those turns that are not performed simultaneously, right? So this is a graph representation of this road network, but remember this is a partial representation. I have not mentioned all the edges explicitly. Now so far, now what we have done, we have converted this traffic signal problem to a graph, right? Now the next task is to store it in the adjacency list, which we can use very conveniently. Now let us stop this discussion for a while. Rather, we are not going to stop, we are going to pause this discussion for a while, right? I will come back to this thing, but before that let me tell you a different concept, right? I will be coming back because that concept is connected with this one. Now there is a concept or there is a problem which is called the graph coloring problem, right? So the graph coloring problem is a very well-known problem in graph theory and mathematics and computer science. Basically, computer science has been extracted from mathematics. So graph coloring is a very popular problem. Where what we do, let me draw a set of nodes, rather let me draw a graph. Here I will drawing nodes of the graph using box, because I just learned how to draw this box, so I'm just feeling like to try this. For example, this is node 1, this is node 2, this is node 3, this is node 4, this is node 5, this is node 6, and this is node 7. And let me connect these nodes. For example, I connect this one with this one with this one with this. Okay, this one with this, this, and this. Now, what is the graph coloring problem? Graph coloring problem says that we have to assign each node a color, right? Such that two neighboring nodes have different color and the overall color which we use are minimum, right? For example, if I give this node a red color, right? Now I cannot use this red color with this node, because otherwise both of the neighboring nodes will have the same color. So in the graph coloring we have to use different colors for same neighbors, right? Now let me use yellow color for this, right? Now if now here I cannot use yellow color, so I will be, because neighbors will have, so I'm using pink color, right? And here I cannot use pink color, so let me use orange color, right? And here let me use white color, it's sort of white. So here I can use, let's say, green color, and here maybe I can use blue color itself, right? Now so here in the graph coloring problem we need not to assign same colors to neighboring nodes, but another constraint here, and for that let me replicate this graph here. For example, this node, this node, this node, this node, this one, and this one, and let me draw the edges as well. Right, and it's the same. Now let me color the same graph with different set of colors. For example, I give this node a red color, which is fine. I cannot assign red here, so what I will do is I will assign red here because these two nodes are not connected directly with each other, so they can have same color, right? And I can give, let's say, yellow color here. Okay, I cannot assign yellow color here, but I can give yellow color to this node, right? Similarly, orange, I can give orange to this node. Okay, and I'm not giving orange color to this node, I'm giving orange color to this node, and let this node be white. Now if you see here, here we have colored the complete graph using 1, 2, 3, 4, 5, 6, 7, 7 colors, right? But in the in the case of bottom graph, we have colored the complete graph using 1, 2, 3 and 4 colors, right? So both of these problems have been solved. Both of these graphs basically follow the graph coloring, but overall goal is to color the graph in such a way that the no two nodes get assigned same color, plus we get to use the minimum possible number of colors. So among these two solutions, the bottom solution is the better solution, right? I'm not saying the above solution is wrong, that is correct as well, but the better solution is the bottom one, right? So this is a graph coloring problem, right? And there are other definitions as well, which will be coming shortly, but this is how we explain the graph coloring problem. So let me go to the slide. Let me just read out so that I may not miss any point. The coloring of a graph is assigned. Coloring of a graph is assignment of colors to each vertex of the graph so that no two vertices connected by an edge have the same color. Our problem is of graph coloring of incompatible terms. I will be coming to that later. So at present, let's ignore it. Now, then there is another concept. Remember, we had paused this traffic light problem for a while. I'll be connecting everything soon, but we went to the graph coloring problem. Now let us come to another concept, which is called the NP complete problems, right? NP complete problems are a set of problems which rather, okay, let me, because it's difficult to make you understand this concept online, but let me try. That is my test as well. Now see here, okay, there must be some definition to algorithms, so data structures or algorithm. I cannot find it, but let me. Okay, it's not here, no problem. It will be in the next lecture. Yes. Now, what is an algorithm? An algorithm is a finite set of statements that guarantees an optimal solution in finite interval of time, right? Now, this is fine. Now, for example, I have a problem which says that to create a timetable, right? You have to create a timetable. University, right? So when you create a timetable for the university, the timetable, the algorithm should execute in finite set of statements. It should guarantee a solution, and the solution should be what? Optimal. And in the timetable, a timetable is optimal timetable which has zero clashes, right? But to make such timetable, if we write an algorithm, it is most probably going to take n factorial time, right? It is going to take order of n factorial time, right? If we write an algorithm, right? We cannot wait that long. But there are certain computers on which such problems can be executed in order of one time, right? So the question is, on which computers thus does such problems get resolved in order of one time? Such computers, rather every computer has memory and processor, right? Such computers on which these problems can be solved in order of one time have infinite memory and they have infinite processing power, right? But now the question is that from where can you purchase such computers? Maybe you can get you go to Hafiz Center, I think it's in Lahore, or maybe you go to Blue Area, I think it's in Islamabad, or there is another plaza in Rawalpindi called, I think, Dubai Plaza or what. They're popular for selling computers and computing stuff, etc. So you go to some shop and you tell them, I want to purchase a new computer, and he says, okay, what is your RAM requirement? You say infinite. And he says, what is your processor requirement? You say infinite. Next thing, he's going to open the shop's door and will ask you to leave, because there is no such computer with infinite processing power and infinite memory, right? So these problems, the problem of timetabling and the graph coloring, they come under the domain of NP complete problems, right? So these can be solved in order of one time on a computer which is non-deterministic. All the computers which we have here with ourselves, for example, if you consider your home PC, it has deterministic amount of RAM, deterministic amount of processing power. So that is why to solve such problems it will take order of n square or order of n cube time. But if we have a non-deterministic computer which does not exist in reality but in hypothesis or in theoretically we can have such computer. So on such computers these problems get solved in order of one time. So this graph coloring problem is also an NP complete problem. Now I'm going to connect this thing, like I'm going to connect NP complete and graph coloring and this traffic light problem in a little while, but meanwhile another concept has popped into my mind which is called the optimization problem, right? Optimization problem. Now these optimization problems are a set of problems which have 3 or 4 properties. Let me write, right? Optimization problems have more than one solutions. 1, 2. Each solution is correct, right? And 3, each solution has a cost. And 4th, we have to select a solution with max or min cost, right? You might be confused in a few things. I'll be connecting all of the things shortly, so please bear with me. Now let me give you an example. Let me give you the graph coloring example itself. For example, this is a graph where and let me make 2 versions of the graph, right? And I connect all of the nodes with each other. I replicate this graph, okay? I'm giving you an example of the optimization problem. So I'm trying to make an example so that you can better understand it. Now, for example, we color this graph. I use red here color here, I use blue color here, right? I use, let's say, pink color for this node because I have to follow graph coloring, and let it be white, right? Then maybe I use pink color here, and I use red color here, and I use, let's say, blue color here, and let me use blue color here, and then I can color this graph using blue color because I'm not assigning same color to adjacent nodes, and I'm assigning this graph. Now, this graph has been colored using 4 colors, right? This graph has been colored using 3 colors, and this graph has been colored using 2 colors. Now let me read the properties of an optimization problem. One, for an optimization problem there are more than one solutions. Now graph coloring, let me write here. In the graph coloring, the simple constraint is that no two adjacent nodes should have same color. Now I have colored this graph. This is solution is correct. This solution is correct, and this solution is correct as well. So we have more than one solution. Each solution is correct, right? And thirdly, each solution has a cost. If you see here, the cost here is 4, the cost here is 3, the cost here is 2. And finally, we have to select a solution either with, this should have been max, sorry, with the, okay, let me fix it, with maximum cost or with the minimum cost. Here we need to save colors, so we are going to pick this option, right? So the optimization problems are such problems where we have more than one solutions. Each solution is correct, each solution has a cost, and we have to select the solution with maximum or minimum cost, right? So graph coloring is an example of an optimization problem. Similarly, if we talk about timetables, timetables. So if you consider timetables, so every timetable, we can have multiple timetables in a university or in a department, okay? And the cost in terms of timetable will maybe the number of clashes. For example, one timetable has 20 clashes, the other timetable has 3 clashes, the other timetable has 2 clashes, right? So the one with the minimum clashes will be the better timetable. So the timetabling problem is also among the optimization problems, right? So I've told you about NP complete, and remember I have not connected all of these. I've opened 3 or 4 topics simultaneously, but I will be connecting all of these shortly. So if we end up writing an algorithm, which is this one, if we end up writing an algorithm for the optimization problems, so these algorithms which will be written for optimization problem cannot solve the solution in polynomial time. Now what is polynomial? For example, if an algorithm has complexity of n square, this is polynomial. If an algorithm has a complexity of n log of n, this is polynomial. But if the algorithm has a time complexity of order 2 raised to power n, or it has a complexity of order n factorial, now these two are not polynomial. But when we try to write an algorithm for the optimization problem, the optimization problem will be solved in exponential or non-polynomial amount of time, right? So what we do is that we do not write an algorithm for the optimization problem. Rather, what we do, we compromise on one of the things in the algorithm, which is optimality, right? Now when we compromise on the optimality of the algorithm, this algorithm actually does not remain an algorithm, it becomes a heuristic. So heuristic is an algorithm in inverted commas which compromises on the optimality of the solution, right? So an algorithm that quickly produces good but not necessarily optimal solution is called a heuristic, and we always write heuristics for optimization problems, because if we write an algorithm for optimization problem, they will not be solved in polynomial amount of time, right? Now coming to coming back to the graph coloring problem. So this graph coloring problem here cannot be solved using an algorithm, so we will be writing a heuristic for it. Now what we do here is that we simply do one thing. We pick one color, and then we color the vertex with that color, and then we go to the next color, and for example here we pick one color, we pick this blue color, and we will color this node. We will go to the next node and we will see, can we color this blue color here? No, we cannot. So what we do, we go to the next node and we see that okay, we can assign this blue color here. Then I go to the next node, can I assign this blue here? No, I cannot. I go to the next node, I can assign it here. Now I come back to, now this blue color cannot be used any further. Now what I will do, I will change the color, I will use red color. Now I will use red color, then I will go to the next uncolored node, which is this one. I can assign this node red color. Now in this way, this is a heuristic where we have colored this graph using two colors, right? So this heuristic is mentioned here, right? You can see that. Now for example, this approach is a heuristic, and this is a greedy approach, right? I'll be explaining about greedy algorithms later in the next lecture, inshallah. But the greedy algorithms basically does not necessarily produce the best solution, but at times they produce the best solution as well, but they may produce a better solution. Now for example, using the same approach, if we see this graph has been colored using 3 colors, right? And if we were to assign the colors to this graph in a better way, then this graph could have been colored using 2 colors, right? So here we have used 2 colors, and here we have used 3 colors, right? So using our heuristic, this solution has been obtained. However, the best solution in this case was this one. But again, if we write an algorithm to solve to obtain the best solution, it may take order of n factorial time, which is too time consuming. So we obtain this answer maybe in order of n time. So we say okay, give us a suboptimal solution, we will do something with that, but give us the answer quickly, right? So this is how it works. Now I've connected these heuristic with the NP complete problems with the graph coloring, but the problem of traffic light still remains unsolved. So remember, here each node represented one turn, right? So when we have ultimately colored the graph, it means all nodes with the same color, this one and this one. These nodes can be opened simultaneously, right? These nodes can be opened simultaneously, then these nodes or these turns can be allowed simultaneously, and then only this one can be allowed simultaneously. So this will give you minimum phases of a traffic light problem, right? So this was a case study of using graphs. In the next lecture, I'll be covering an algorithm related to searching in the graph. Thank you.